Okay, so welcome back. Last class what we have done, we have derived the formula for Navier-Stokes equation and we have reduced the Navier-Stokes equation for the one dimensional flow. Now, what formula we have derived is dp by dx, or you can say minus of dp by dx if you are writing from final minus initial, will be equal to m naught dv upon dx if you are writing in the flow in the x direction, plus P upon A tau W minus rho into G. Okay. Now, if you are writing in one direction, it can be Gx, I can write rho G, plus and minus is just showing the direction of the gravity. So, in this case, this is what we have said, that the dp by dx, the single phase flow is actually can be reduced in three parts. One is the acceleration term, delta P due to acceleration, another is your frictional term or viscous term, friction, and then gravity term. So, what we have said that this is what the delta P equation is if you want to find dp by dx in a pipeline for the single phase flow. This is what the delta P will be, the contribution will be from acceleration, fluid acceleration, from fluid friction, and because of the gravity field. So, all these three fields will play their role and you will see the combined effect that will be in terms of the overall pressure gradient across the pipeline or across any column for the single phase flow. We have discussed that what is the problem. The problem comes with the tau W, the frictional term, and tau W we have written as F rho u square by 2. So, we said that the problem is with the friction factor, how to find it for laminar flow F equal to 16 by Re, and for turbulent flow we said that you have either Colebrook equation, Blas's equation, or you have to go to Moody chart depending upon E upon D value or K upon D value, which is K is nothing but the roughness factor, you will get the different value of the F. So, that was the challenge in the single phase flow. Now, what we are going to do now is to start writing the equation for the multi-phase flow, and I will start with the gas liquid flow, and we will see that how to write the equation or how to change this equation for the different flow regime. Now, to start with, the first flow regime which we have studied is the homogeneous flow regime. Okay, homogeneous flow. Now, what does homogeneous flow? Homogeneous flow is where both are homogeneously mixed, or you can also say it is a mixed flow. Okay. So, it means both the phases gas and liquid are homogeneously mixed inside and they are flowing together. So, how the whole equation will be modified in case of homogeneous flow. Now, if you think about the homogeneous flow, then what is how we will write the mass balance. So, the mass balance m naught will be written as rho into V into A. Now, we have, this is for the single phase flow, now we have two phases. So, how the rho will be there, and if the both the phases are homogeneously mixed, it means suppose this is the pipeline, both gas and liquid are homogeneously mixed, okay, and they are flowing together. So, because they are now behaving as a mixture, so I can reduce it in terms of the mixture density. So, I will write it rho m, where rho m is nothing but the mixture density. Okay. So, it means what? Instead of writing the equation, two equations for both the phases, I can write the equation in terms of the mixture density, mixture velocity, or it because both the phases are homogeneously mixed, instead of considering them as a two different phases, I can consider them as a single phase, and I can take the property which will be the property of the mixture. So, the overall mass balance equation or continuity equation, we can write it as a rho m into V into A, and V is what? V will be of mixture velocity. So, V m. So, this will be the mixture velocity. Now, the problem is how to find the mixture velocity, how to find the mixture density. If we know that, then we can find it out, we can write the continuity equation at least. So, for mixture density, how we write that rho m of, it means the mixture density is nothing but epsilon of L into rho L plus epsilon of G into rho G. Okay. So, it means volume fraction of liquid phase inside the pipeline multiply by the density of, this is the fraction or volume fraction of liquid. Okay. This is density of pure liquid similarly this is volume fraction of gas and this is density of gas. It means if I know the volume fraction of the liquid, if I know the density of the liquid, then if I know the volume fraction of gas and density of gas, I can find it out the rho m, and we know that the formula one more, and that is epsilon L plus epsilon G, this is equal to 1. So, if I know either epsilon L or epsilon G, I can find it out that what will be the, and if I know the density of pure species or pure liquid and gas, then I can find it out the rho m. Now, the problem is that how to calculate the rho m, how to calculate the epsilon L. So, we know that volume fraction is being defined, say liquid volume fraction is defined as a volume of liquid upon volume of reactor, or I will say column, say a pipeline. Okay. So, this is the way we have already introduced the volume fraction epsilon L, and that is nothing but the volume of that phase divided by the total volume. So, that is the way we can find it out, that epsilon L. Now, volume of liquid is what? Suppose the cross section, this is a pipeline and a particular fraction, or this is suppose the area of the pipeline, and particular fraction in the area has been occupied with the liquid. So, in that case I will say that to simplify it, I can say this is AL, it is the area of liquid which has been occupied multiplied by the length of the pipeline divided by the total area, total volume will be what? Area, cross sectional area into L. It means because they are homogeneously mixed, I am assuming that a particular fraction in the pipeline, a particular area fraction has been occupied by the liquid, and that is remaining same throughout the length of the reactor. So, this will be AL into L. Now, this AL can change with the length of the column, but that overall value of AL remains same. It means if I am saying that 60% of the area is being occupied by the liquid, that 60% may change. So, that 60% can be distributed like this, that 60% somewhere can be distributed like this, that 60% somewhere can be distributed like this. So, that distribution may change over the length of the reactor, but that AL remains same, the fraction of the area which is being occupied by the liquid is remains same. So, I can write it epsilon L by this, or I can write it as a AL upon A. If length will be cancelled out, you will see AL upon A. Okay. Similarly, you can write epsilon G similar way, and epsilon G will be nothing but the AG upon A. So, if I know the fraction of the area which is being occupied, I can find it out the epsilon L and epsilon G, because area we know already, that is the pipe area. Now, the problem comes with the mixture velocity. So, Vm. Now, Vm is what? Vm will be nothing but it is the flow rate of or superficial gas velocities of liquid plus superficial gas velocity of the gas. So, why this way we can write? Because total mixture flow rate, say Qm, if in the pipeline we are sending gas and liquid, say gas flow rate is Qg, liquid flow rate is QL, then Qm mixture flow rate will be what? Qg plus QL. Okay. Now, if I want to find it out the mixture velocity in terms of the superficial velocity, because that is only mixture is which is being filled inside the column, what I can do? I can divide it by the area. Okay. If I divide it by the area, what I will get? This will be Qm upon A, it means flow rate, mixture flow rate divided by the cross sectional area, it will give me the UM or VM. Let us denote it with the V because we are following the notation V. So, this will be VM, where VM is what? Nothing but the superficial and I hope how you know that how to define the superficial velocity. Superficial velocity is nothing but the volumetric flow rate divided by the area of empty column. It means you are not considering any internals, any other thing, only the area of the empty column. We divide with the volumetric flow rate, we get that superficial velocity. Okay, that is why this name is called superficial. Similarly, if you Qg is the flow rate, we are knowing that how much of the gas flow is going in, gas volumetric flow rate. This will be written as, this will be equal to V into G, where Vg is nothing but superficial of gas. It means what? We are assuming only gas is flowing inside the pipeline. What will be the velocity of the gas? That is called superficial velocity of the gas. We are neglecting the liquid fraction. It means we are assuming the whole pipeline is only filled with the gas. Similarly, this term will be equal to V of L, where VL will be nothing but superficial velocity of liquid. It means we are assuming that only liquid is filled inside. So, it means what? We have found the correlation for the Vm. Vm is nothing but Vg plus Vl, and if we know that what is the volumetric flow rate through which the gas is flowing inside the pipeline, if I know the volumetric flow rate of the liquid, I can find out the mixture velocity, and mixture density I can find it out if we know that Ag upon Al, then we will know the mixture velocity. Now, in that case, what will happen? We can write the continuity equation and we can solve it. So, at least the continuity equation portion we can solve. The only problem is to find that Al and Ag. These are the two problems to find, that how to find what is the fraction of area which is being occupied by the gas, what is the fraction of the area which is occupied by the liquid. So, if we know that, we can at least solve the continuity equation. Now, if you write the momentum equation or velocity equation for the homogeneous model, what I will do, I will just write first that dp by dx, this will be equal to minus in terms of, now I am writing first for individually two phases, okay, and both are flowing together. So, I will just reduce the term. This is for the single phase, single term we have written. Now, I will write the two terms and then we will try to combine them. It means what? I will write it the tau Pg, instead of this I will write Pg upon A. It means perimeter of the gas, which is the perimeter which is being occupied by gas, upon tau Wg. It means wall shear stress because of the gas, plus I will write PL upon A, tau WL. Okay, it means wall shear stress because of the liquid, okay, plus the gravity term will write it as a rho g epsilon g plus rho l epsilon l into g, because we have to write the mixture viscosity, mixture density. Instead of mixture density, I am writing these two terms. Okay, so this will be the rho g epsilon g plus l, and then we have to write the momentum term or acceleration term, and acceleration term is nothing but we will write it as a d by dx. We are writing it in terms of the V of gas. Okay. Ideally, it should be what? The liquid velocity inside, we will write it as a Vg right now. If you write it into the Vg, you have to write the V into dV upon dx. So, we were writing it in terms of V or m naught of gas into dVg upon dx plus m naught of liquid into dVl upon dx. Okay. So, you can write it out, what is the mass flow rate of the gas which is coming inside, what is the mass flow rate of liquid which is coming inside in terms of the VL. Okay. Now this should be ideally what? It should not be the superficial velocity, it should be the inside velocity, and because it is inside velocity, I am going to write it in terms of not with the v, I am going to denote it in terms of the u and this ul, okay, which is ul and ug shows the velocity of the gas and liquid inside, okay. So this is the actual velocity. Liquid inside. Okay. Similarly, this will be the actual velocity of the gas inside the pipeline. Now, what we can do? We can work on these terms, these two terms particularly. So, I will write it as this term m naught g. I can write it in terms of what? It will be nothing but rho g into Vg, okay, into area, where Vg will be nothing but the superficial velocity, okay. Now, d by dx of ug, you can write it in this way. Now, if I divide it by the area, okay, then what will happen? Because we have already divided by the area, this is m naught upon a, this is upon a. So, this a and a will be cancelled out. So, what you will get is rho g into Vg. Now, we can write it in terms of this as a d by dx rho g into Vg, okay, upon ug. Now, we have already said that what is the ug and u correlation, Vg correlation. So, we can write it out, Vg upon epsilon is nothing but ug, okay. This we have already discussed. It means what? The inside velocity will be nothing but the superficial velocity divided by the volume fraction of the gas inside the pipeline. That will be what? The inside velocity of the gas you will see, because this is what? Vg is what? Superficial velocity. Now, superficial velocity, how we have derived this? We have already discussed, but just again one for the revision. So, this is suppose the pipeline. What we have assumed while calculating the superficial velocity, which is Vg, Vg is nothing but Qg upon area, okay, and we have assumed that complete area is being filled with the gas. Now, Ug is what? Ug is Qg upon area of gas, okay. Now, area of the gas, what we know that this is the cross sectional area, some portion is being filled by the liquid, say, and some portion is being filled by the gas. So, what will be, you can write it, you can write that A, we have already seen that epsilon g is nothing but, we have already seen that epsilon g, I have just shown here that epsilon g is nothing but Ag upon A. So, it means what? A you can replace it as, A is nothing but Ag upon epsilon g, okay. So, you can write it in terms of what? Now, if you reduce this equation, it means what? You can write Vg, which is nothing but Qg upon area, okay. Now, area can be written as Qg into Ag into epsilon g. Now, this value is what? Qg into Ag is equal to Ug, okay, into epsilon g is equal to what? Vg. So, you can write it out, Ug will be nothing but Vg upon epsilon g, okay. So, by using that, what I can do? I can change this differential and I can go this as a rho g into Vg d upon dx, and instead of Ug I can write it out as a Vg upon epsilon g. Now, if I just solve this equation, I can write it as rho g into d by dx, and I can write it out as a Vg square upon epsilon g, okay. So, or if I can put it rho g also inside, so I can write it as d by dx rho g into Vg square upon epsilon g. Similarly, for the liquid also I can reduce the same term. So, this term is equal to what? This term was equal to rho g into Vg into dUg upon dx. This I can write it in this form. So, what I can do? I can write similarly rho L into VL dUL upon dx can be written as d by dx of rho L into VL square upon epsilon L. So what I can do, again I can write the equation for the dp by dx in this form. So minus dp by dx will be equal to Pg upon area tau Wg plus PL upon area tau WL plus rho G into epsilon G plus rho L into epsilon L gravity, plus I can write it d by dx, and this will be rho G V square G upon epsilon G plus rho L V square L upon epsilon L. So this will be my equation for the homogeneously mixed two-phase flow. Okay. Now we have not assumed that both the phases are moving with the same velocity or something. We have said that this is the general equation of homogeneous flow, where both the phases are flowing together. Now this will be nothing but the frictional term due to gas. This is frictional term due to liquid. This is gravity term due to gas. This is gravity term due to liquid. This is acceleration due to gas, and acceleration due to liquid. So what we are saying, if the flow is homogeneously mixed, what we will see, you will see the dp by dx. Now instead of the single phase flow, whatever you are seeing, that the overall dp by dx is a function or is the summation of the dp by dx occur because of the friction, dp by dx occur because of gravity, dp by dx occurs because of the acceleration. Now you will see the effect which will be the combined effect dp by dx, which will be frictional term, but the friction will be now caused because of the gas and liquid both. So this two terms has been kind of written. The gravity term which will be because of the gas and liquid both, so this term has been added, and acceleration term again that will be because of the gas and liquid, which is because that this term has been added. So this is the general equation for the homogeneous flow. Now the homogeneous flow, generally what we assume is that the whole flow is flowing as a mixture and there is no slip in between. So homogeneous flow with no slip, that is mostly we write it in that way, that homogeneous flow with no slip. Now what do you mean by no slip? No slip means there is no slip between the two phases inside. It means if both the phases are flowing inside, say gas and liquid, so gas and liquid both are flowing inside. Okay. I am writing the gas in form of the bubble. There is no slip in between. It means what? Ug is equal to UL. It means the velocity of the gas inside the column is equal to the velocity of liquid inside the column. It means there is no slip in between. So what will happen? The velocity remains same. If the velocity remains same, it means what? Now you can write it out, the mixture velocity and everything you can write, because both are the velocity is same, you can write everything in terms of the mixture velocity. Now how the mixture velocity we can write? We have already shown that Ug or V of G, mixture superficial velocity, is nothing but velocity of superficial velocity of the gas plus superficial velocity of the liquid, or you can say Qm is nothing but Q of G plus Q of L. You can write it in this way. So what happens with the no slip? No slip means it says that phase hold up is equal to phase volume fraction. Okay, that is what it means. Now there will be confusion, bit confusion. We have already discussed what is volume fraction. Volume fraction is being denoted by epsilon g and epsilon g or epsilon, and phase hold up is defined by alpha. It means what we are saying, that alpha will be equal to epsilon. Now how the phase hold up has been defined? Epsilon we have already seen that how the epsilon has been defined. So epsilon has been defined as volume fraction of that phase divided by volume of reactor. I will write column. Okay, volume of column. Now how alpha is defined? Alpha phase hold up is actually being defined the way the liquid or the gas or the different phases are going inside. It means what? Alpha is nothing, will be defined, say alpha of G will be defined as Qg upon QL plus Qg. So what we are saying, that if there is no slip and the phases are distributing according to their flow rate inside, then what will happen? The alpha G, the fraction, the phase hold up inside, the gas hold up will be inside, will be nothing but what is the volumetric flow rate. Now if you will see here the volumetric flow rate, that is what we are saying, there is no slip. It means both are being occupied same, there is no velocity difference inside, and they are being kind of occupied the fraction according to their inlet flow rate. Okay, so that is called phase hold up. And if their fraction occupied inside is equal to the according to their inlet flow rate, it means the phase volume fraction, which is the volume fraction inside the reactor, is equal to the phase hold up, which is the hold up or the fraction of the gas which is being fed compared to the total flow rate. So this is the Qg, it means this is what is the gas flow rate divided by the total flow rate. So Q, this is nothing but the mixture. So I can write it as Qg upon Qm. It means the hold up is defined as what is the fraction of flow rate of the gas divided by the total flow rate. It means the fraction of the gas flow rate divided by the amongst the total flow rate. Okay. So alpha G, if suppose 60%, it shows it was that the fraction of the gas at the inlet is 60% and 40% is the liquid. It means the total flow rate, if I know, I will just multiply by 0.6, I will get the gas flow rate. If I multiply by 0.4, I will get the liquid flow rate. So that is what alpha G is there. And if there is no slip inside, it means both the phases is being flowing together without having any difference in the velocity. So what will happen? Their phase hold up will be equal to the volume fraction. It means they will be there inside of the column, they will occupy the similar fraction as per their flow rate. So if you do that, this is actually the same. If there is no slip, then what will happen? This is nothing but the volume of gas and this is the total volume. Okay, the time will be cancelled out. So you will get that epsilon. So if there is no slip, alpha will be equal to epsilon. It means they will be distributed exactly same way as they are coming in. Okay. Generally this is a condition, a very big assumption which is being there, and very small cases, percentage of the cases you can see the homogeneous flow with no slip condition. We will see those cases which are being used for such kind of a flow. So once I say homogeneous flow with no slip, it means what I am meaning, that alpha is equal to epsilon. Now because alpha is equal to epsilon, I can write everything in terms of the um, because I know the um now. Okay, I can calculate the mixture velocity, so I can write everything in terms of the um. Okay, and that the way we write it, now what we will do, we will write everything in terms of the um, and Vm or Vm we have already said is nothing but Vg plus Vl. And if I know the flow rates, individual flow rates, I will know the mixture flow rate, or if I know the total flow rate, anyway I am knowing the Vm. So what I can write? I can write the complete equation like a single phase flow equation, and I will say minus dP by dx is nothing but will be equal to P upon A. Okay. Now this will be tau m, okay, W plus, I will write it rho m into G plus it will be rho m into d by dx of u m square. Okay. Upon epsilon g term will not come, it will be upon this. So, I can write it as in terms of the earlier way, the way we have written, and that will be, you can write it as m naught of mixture divided by area into d V m upon dx. Okay. Or if you write, you can also write it this term as, instead of this you can write it as a rho m into V m into d V m upon dx. So, whole equation will now be reduced it in this form. You will want to write in terms of the mixture mass flow rate, or you want to write it in terms of the rho m, you can find it out. Now, the thing is that you now calculated, you reduce everything in terms of the single phase flow, and because there is no slip, you can easily write everything in terms of the mixture flow rates. Okay. And this tau m is nothing but the mixture frictional, this is the friction term, this is the gravity term, and this is the acceleration term. Okay, and you are writing every term in terms of the mixture. Now, the problem here is, what is the problem? Again, the tau m is going to be the problem, rho m is going to be the problem. So, rho m we can now calculate. Now, rho m is no more a problem actually for homogeneous flow with no slip, because I can write it out rho m as rho L into epsilon L plus rho G into epsilon G. Now, because epsilon L is equal to alpha L and epsilon G is equal to alpha G, it means the volume fraction and phase hold up is equal. Rho m can be written as rho L into alpha L plus rho G into alpha G, rho G into alpha G. So, now we know the alpha G, we know the alpha L, we know the individual density of the both liquid and gas, the rho m we can easily find it out. So, that the problem, one problem we have reduced and we have simplified it. So, we can find it out this rho m very easily, this value. V m we can anyway find it out. So, this value we can also reduce, find. Now, the problem comes with again tau m w. Now, tau m w will be written as what? Again same friction factor, which will be based on the mixture, okay, into rho m into V m square upon 2. Now, again rho m we know, V m we know, the only problem is with the F m, and now the F m problem becomes little bit more severe compared to whatever we were facing in the single phase flow, because let us assume that this is a laminar flow. So, F m will be written as 16 upon R e, and this R e will be based on the mixture Reynolds number, and mixture Reynolds number R e m will be defined as V m into rho m, okay, into diameter of the pipe divided by mu m. Now, this is the problem in single phase flow. We know the mixture viscosity, we know the single phase flow viscosity, the fluid viscosity, we know the fluid density, V m and V and D we already know. Here we know the V m, we can calculate it if we know the total flow rate divided by cross sectional area, we know the V m, we know the rho m because we know the alpha G and alpha L. The only problem is mu L, that how to calculate the mu m. So, the mixture viscosity calculation itself is a very big task, and it is a whole field of rheology, and I am not discussing that, but if you will go and see any petroleum field or any phases, the rheology field, you will see that finding the mixture viscosity itself is a big challenge, and it cannot write, you cannot write it in a very simple form the way we have written rho m, but for a better approximation or for the first hand approximation, the mu m can be written as the way we have written the rho. But this is the very big approximation and has been found true for a very few cases. Most of the cases this is not true, and that is why what you need to do, you have to depend on the mu m on the experimental data. It means if you are homogeneous model you are using, at least one thing you need experimentally, and that is the mu m, that what is the mixture viscosity. you have to use the viscometers, Brookfield viscometer or any other type of viscometer to find it out the mu m, or you have to go to the field of rheology, you have to develop the equations for the mu m for different composition. Now, the problem is that mu m, suppose if I am talking about oil transportation pipeline, each crude oil have a different property. Even with the hour or with the time, this viscosity, the property of the crude oil changes. It means the viscosity of the crude oil will change. So, every time you have to go and find it out that what is the value of mu m if you want to use the mixture model, homogeneous model, or also known as a mixture model. So, this is the complete formulation of homogeneous model with no slip condition, okay, where the no slip condition, again I am saying that the phase hold up is equal to the phase volume fraction. It means there is no slip in the inside. So, this model, this kind of a model is being used when the rho L upon rho G is less than 10, and as you can see that rho L upon rho G mostly have a difference of 1000, other than the petroleum industries where this is true sometimes. The rho L upon rho G is less than 10 or the m naught is greater than 2000 kg per meter square per second. Okay. So, only for these conditions this homogeneous model is valid, which is true for oil gas transportation. So, in that oil gas production and transportation one can use the homogeneous model, but most of the places because of these two limitations, particularly this, the homogeneous model with no slip condition is not valid, and one has to go with more rigorous model to understand that how to calculate the dP. So, in homogeneous no slip model I hope you will now able to calculate the dP and how the equation has been simplified and how we have done this job. So, with this we will stop today and we will discuss the other models in the next class. Thank you.